Hello everyone, it's Double A here. Today we're going to be exploring a typical residential coaxial cable TV and internet line with the RTL SDR USB and Spectrum Analyzer software. Now, the first thing to consider is how coaxial broadband networks actually work. So let's discuss that. Now, if you have Comcast, Spectrum, or another broadband provider that delivers your internet and TV over coaxial cable lines, chances are you are a part of a hybrid fiber coaxial network. An optical node might be located at the entrance to your neighborhood, on your street block, or in your apartment building, depending on your area's population density and the speeds the provider wants to offer. High bandwidth fiber optic cable goes to this node. And then, from this node to the individual homes, businesses, or units, coaxial cable is run. A single coaxial cable is often split many times, and RF amplifiers are often also needed to boost the signal throughout the entire service area of the node. Historically, cable network operators only delivered linear TV, so only one-way amplification was needed. Today, interactive content such as internet and phone service is delivered, so two-way amplification is required. The problem is, traditional amplifiers are one-way devices. If you were to place two amplifiers in this configuration without any sort of filtering, you would get a nasty feedback loop, and no data could be transmitted through the line. So the solution is to use radio frequency filters to only pass some frequencies towards the customers and only pass others back towards the cable company. The question then for a cable network operator is, where do you put that split between the frequencies that go to the customer, or the downstream, and the frequencies that come back from the customers, or the upstream? Early two-way networks were sub-split. Little upstream bandwidth was needed, maybe for phone calls, telemetry from TV boxes, a viewer request to watch on-demand or pay-per-view content, and maybe, by today's standards, slow internet. As internet traffic has increased, and lately since COVID spurred the work-from-home revolution, customers are demanding faster speeds, and especially faster upload speeds. Cable network operators are upgrading their networks to be mid-split and high-split. Even today, still, upload speeds are typically slower than downloads on internet delivered by coaxial networks. And for mid-splits, and especially sub-splits, this asymmetry can be quite severe. For example, on my Comcast mid-split, I get about 300 down and 10 up, which are the advertised speeds. And if you look at the bandwidth dedication to scale, you can see why that is. So, how can cable internet upload speeds be improved? Well, cable operators can allocate more bandwidth to upstream, that is, by upgrading to mid-split or high-split, but this can be costly as all amplifiers on the node need to be replaced to accommodate the split change. Additionally, user equipment like TV boxes may need to be replaced if it expects to receive control signals on a frequency that is reallocated to upstream. I believe this is an issue if Comcast wanted to upgrade nodes to high split. A cable operator can upgrade to newer technology that provides more spectrally efficient signaling methods, for example, DOCSIS 3.1 instead of DOCSIS 3.0, but cable internet users' modems still need to be replaced to see the faster speeds. And Shannon capacity limits still govern the maximum data rate of the channel if it has a fixed bandwidth. Cable companies can also bring fiber optic cables closer to the customer, so fewer customers are sharing each node. Of course, though, it is costly to run new fiber optic cable and install new nodes. And be aware that cable companies are doing all these things, just when they have such large service areas and shareholders may be more important than customers, rollouts can be slow. As far as required hardware goes, you'll need a reasonably fast Windows computer, the RTL SDR USB, and I recommend using it with a USB 2.0 extension cable because the USB is kind of big and could potentially break a USB port, at least on a laptop. You also need an SMA to coax adapter to connect the coax cable from your cable company to the SMA connector on the RTL SDR. Of course, a coax cable to plug into your wall, and you might also want a coaxial splitter so you can maintain your internet service by keeping that coax connected to your cable modem while you do this testing. As far as software goes, you will need the driver for the RTL SDR USB and the Spectrum software. If you've already installed either of these, you can skip ahead using the chapters in the video. To install the driver, you want to go to this website, which is also linked in the description, and scroll down to the SDR Sharp Setup Guide header. Under here, click the link to download the Microsoft .NET 5.0 32-bit redistributable. And you might have to click to download manually. And save that installer to your downloads folder. Once it's finished downloading, you're going to want to run that installer. And click install. You might have to click yes to a confirmation prompt. And once it's done, you can close out. Next, you're going to want to install the AirSpy software-defined radio package. So click the link to go to airspy.com, click download, and you're going to want to download the software-defined radio package. And go ahead and just save that to your downloads folder. Next, you're going to want to right click and extract all. And you're going to want to double click install-rtlsdr.bat. Once that's finished, you can just push any key and it will exit the command prompt window. And next, within that same SDR Sharp folder, you're going to want to right-click zadig.exe and run as administrator. You might have to click yes to a confirmation prompt. Now, in here, you're going to want to click on Options, check List All Devices, and then uncheck Ignore Hubs or Composite Parents. And then click the drop-down and select Bulk in Interface, Interface 0. Be very careful to ensure that you're selecting this option. And then you'll want to confirm that USB ID is what is displayed here. And next, you're going to want to click Install Driver. It might also say Replace Driver instead of Install Driver, in case Windows automatically installed a different driver previously. Next, you want to go to this website, which is also linked in the description. And then you want to scroll down and download the latest test build from here. Now I'm going to download the not Linux version because I'm using a Windows machine. And download. And I'm going to save that as, and save it into my downloads folder. So I'm going to open my downloads folder, right click on Spectrum SV mod, and extract all, and extract. Now let's find the extracted folder, open the Spectrum folder, and run spectrum.exe. Windows might block it the first time, so just go to More Info and run anyway. And now, if you've installed the driver to your RTL SDR stick, it should show up right here, and just double click that. Now, by default, Spectrum appears to be set to the FM band, or 88 to 108 megahertz. And the first thing I would do is go to the Measure tab and turn this gain down to 0. What's interesting here in the FM band, I can still see what appears to be 2 carriers, and those are most likely actually FM radio stations leaking into the line a little bit, which does happen. especially given that I'm only about a mile away from some high power FM radio stations from their transmitters. And cable companies will often know where these high power transmitters are and avoid using those frequencies on their coaxial lines in areas that they know are very close to the transmitter and would be affected. And a very common thing with the mid split is to actually use the FM band as like a guard band. So they don't use the FM band at all. And the downlink is above the FM band. The uplink is below the FM band. I'm going to go back to the setup tab and set my start frequency as 5 megahertz, or it wants units of hertz, so that's a 5 and 6 zeros. And my end frequency as 900 megahertz, or 900 and then 6 more zeros. And set range. And now my signal actually appears pretty weak, so I'm going to give a little bit of gain. And now I can say pretty confidently that I can see what's going on my coaxial line. Because there's amplifiers that are only boosting what's going back to the cable node or back to the cable company, I'm not going to see so much upstream data because a lot of that is not being amplified in my direction. But I am seeing all of the downstream usage because that's being amplified towards all the customers. So it appears that the downstream, which you can see right here, is beginning at about 108 megahertz, which is standard for a mid-split. And what we can see here, each one of these are spaced by 6 megahertz. These are single carrier QAM channels. Originally they were used for a digital cable when analog cable went away, because digital cable is much more spectrally efficient. You can put multiple sub-channels into one 6 megahertz channel, which you couldn't do with analog. With analog cable, each 6 megahertz was one TV channel, and that was it. So by switching to digital cable, it allows Comcast or Spectrum or whoever to put multiple virtual channels onto one 6 megahertz physical channel. And that frees up more bandwidth for them to offer high-speed internet services while still offering the same number of TV channels. And digital TV allows for high definition, which wasn't possible in the analog days. Now, just from looking on here, these 6 megahertz channels could either be for TV or actually a downstream internet. DOCSIS standard 3.0 and earlier just used standard 6 megahertz channels, but instead of television data going over them, it's internet data. Now we can see here what appears to be some unused spectrum, and actually I found by digging a little deeper, this is spectrum that is still being used for some unmodulated analog video carriers. There's no video going over them. And then this here is a 6 megahertz just unused channel. And then up towards the higher end, you can see what appears to be some contiguous spectrum use from about 672 megahertz up to 766 or so megahertz. And this is actually a large OFDM channel, or orthogonal frequency division multiplex channel, that is used for DOCSIS 3.1 internet for customers who have compatible modems. And the OFDM basically uses a contiguous set of frequencies. There's no gap at each 6 megahertz interval, and it's more spectrally efficient. So for customers with supported modems, they can achieve faster download speeds on DOCSIS 3.1 as compared to DOCSIS 3.0, which just uses the 6 megahertz single carrier QAM channels. Let's zoom in to a single carrier QAM channel just to see what it looks like more closely. So let's go from 106 megahertz up to 122 megahertz. Go back to setup. Okay, so now we can see two and then the edge of a third single carrier QAM channel. So this first single carrier QAM channel has a center frequency of 111 megahertz and a bandwidth of 6 megahertz. So it spans from 108, the very top of the FM band, to 114. And then again, we have another 6 megahertz single carrier QAM channel centered at 117 megahertz. and so on. We have these channels at 6 megahertz spacing. And in Europe, these are generally at 8 megahertz spacing. The reason being, analog TV in the United States was historically spaced. Each channel was spaced 6 megahertz apart, whereas in Europe, that spacing was 8. So those two spacings still kind of continue till this day. And let's take a look at I'll call it gunk, that resides between about 436 megahertz and 450 megahertz. And we're getting some peaks that are going off the chart, so I'm going to lower the gain here. And we notice one lies at about 439.25 megahertz, and the other lies at about 445.25 megahertz. And interestingly enough, these are the frequencies for American cable TV channels 60 and 61. More specifically, these are the frequencies for NTSC video luminance, or brightness carriers, on those channels. And what's interesting, when I tune my TV set to those two channels, instead of static, I actually get a black screen, which indicates that Comcast is still transmitting unmodulated video carriers on these two TV channels, which I imagine is just a relic of the past. What does kind of stink, not that it's a huge deal, but this is 12 megahertz of bandwidth that is being wasted on a literal black screen. But I thought it was interesting to find. I was not expecting to see analog video still on a coaxial line in 2022. So let's zoom in on this OFDM channel used for the DOCSIS 3.1 high-speed internet. So we'll go from 668 megahertz up to, say, 780 megahertz. And again, not a whole lot you can see with the RTL SDR, and I'll add a little bit more gain. What you can see is, instead of those like 6 megahertz channels that were discrete, they had a little bit of spacing between each one. This is just one big contiguous channel. And you can read about orthogonal frequency division multiplexing. It is regarded as one of the most spectrally efficient technologies developed to date. And it has wide applications, including with Wi-Fi and cellular standards, both LTE and 5G, that's now rolling out. And now I'm going to look at specifically the uplink, or basically everything below about 88 megahertz, below the FM band. So I'm going to go from 5 megahertz to 88. And this just kind of looks like garbage, so I'm going to lower the gain here. Well, what I can do is run an internet speed test and show that some of the uplink spectrum is being used. So let's go. Again, right now I'm connected in with my splitter. So yeah, we can see here. Now, right now we're actually doing the download. So we're still sending a little bit of like telemetry back through the uplink. But now when we do the upload speed test, we see a lot more usage on the upstream side of the spectrum, which makes sense. And the test is over and everything pretty much dies down. So from spectrum, we can't really tell what each of these single carrier QAM downstream channels is used for. However, I was able to use my TV set and my Cable Modems Diagnostics webpage to identify most of them. Although I can't watch the TV channels, at least without hacking them because I'm not a subscriber, when I put it in cable mode and connected it to my Comcast line, my TV signal meter was able to identify which single carrier QAM channels were actually being used for TV. Interestingly, I counted 411 digital virtual channels being jammed into just 41 6 megahertz single carrier QAM channels. So back in the analog cable TV days, only 41 TV channels would have been possible in this bandwidth. Also, perhaps even crazier, in one case I found Comcast jamming 50 virtual channels into one 6 megahertz spot. I believe these are the Music Choice music channels, which require little bandwidth since they're primarily audio with sub 1 frame per second slideshows as the video. Using my cable modem's diagnostics, I was able to identify which SC-QAM channels are being used for downstream internet. Since my modem only can lock 24 downstream channels at a time, I had to adjust its starting frequency and reboot it a few times to identify all 44 DOCSIS 3.0 channels in use. My modem does not support DOCSIS 3.1, so I can't provide any more specific information on that, except that it appears Comcast is currently using 96 megahertz of bandwidth for the downstream on my node. An interesting coax interference problem I solved in part with my RTL SDR occurred at my parents' house, where the History channel and a few other channels they subscribed to were pixelating and sometimes not working at all in the basement. Now, they have Verizon Fios, which brings fiber optic cable directly to the home to an ONT, or optical network terminal, and any TV boxes are connected to this ONT via coaxial cable. When I used the diagnostic tool in the menu on the Fios box, I could identify the frequency those specific channels were on. Then, I disconnected the coax cable from the ONT, not like this though, and connected my RTL SDR to the coax port for the basement TV. What I found was what appeared to be an over-the-air digital TV station there. Sure enough, we were just a few miles from a transmitter, and enough interference was leaking into the line to nuke out the History channel and a few others. So, my quick and easy solution was to put an unused coax amplifier they had in the house just after the output on the ONT. This did resolve the issue. So, thanks for joining me as I go deeper into the realms of telecommunications and broadcasting. And if you haven't already, please consider subscribing. It's free, unlike cable TV.